Hello, Chem 1B. This is Chapter 19, Lecture Video 3, and we're going to very briefly talk about two new units that you may not have known about before, and that's amps and voltage. So an amp is a measure of electrical current, and you should know its relationship to coulombs and time. 1 amp is equal to 1 coulomb of charge, coulomb is a measure of charge, per second. Now, why do we have electrical current? Well, electrical current is typically driven by a potential difference in a reaction. So a cell reaction or a reaction occurring in a voltaic or galvanic cell is driving electrical current through the system. And this is really created by the potential difference or the voltage of the cell. When we have a reaction that's spontaneous, the voltage will be positive, and when it's not spontaneous, it'll be negative. Now, the more spontaneous our reaction, the larger the voltage of that cell, which means the greater cell potential. Voltage, cell potential, they mean the same thing. Electromotive force is another way of saying the same thing as well. So if you see if you're being asked for electromotive force, cell potential, voltage, they all mean the same thing. The larger this value, the more spontaneous the reaction. You should know something about the unit of volts and how it relates to joules and coulombs. 1 volt is equal to 1 joule per coulomb of charge. So you should know that unit relationship. All right. So a lot of what we're going to be talking about here is what's known as either a galvanic or voltaic cell. And these are basically batteries. Now, you can use either of these two words. They're interchangeable. So if you see one or the other, know they mean the same thing. If we bring together species that are being both oxidized and reduced into the same container, the reaction will happen as long as we have a spontaneous process here. Now, at the end of the day, an engineer might look at that and go, well, that was a waste. Because if I take the reduction half reaction and I put it in like a beaker, and then I connect that beaker to another beaker with a wire and what we call a salt bridge, then the reaction will still proceed, but the electrons will have to go through the wire. And if electrons move through a wire, we get electricity. So kind of useful. We can use that redox reduction to then do electrical work, which is super useful. So engineers would be like, no, let's do this instead. Instead of putting them in the same container, let's separate them, connect them with a wire and what we'll call a salt bridge, and this will allow us to generate electricity and use that electricity for work. So for instance, this is the first option, right? If I take zinc metal, this is zinc, right? And I put it in a solution of copper 2 plus, probably copper 2 plus and nitrate, I would assume. This will cause a redox reaction to happen, and we'll spontaneously start seeing the Cu 2 plus go to Cu solid, and the zinc solid will go to zinc 2 plus. And so these are the two redox half reactions. Again, we'd actually need to balance these. This has 2 electrons here, and this has 2 electrons here. But these are our 2 half reactions that are occurring in this system. Now, at the end of the day, this is great. We have a reaction happening. It's spontaneous, but there is no electricity being generated. Well, there is, but we just can't use it. No usable work in this system. So we want to kind of change this up. We can use that same 2 reactions and split this up. Whoops, sorry. So again, the copper metal is going to precipitate. That's the black stuff we see. And the zinc is going to dissolve. So this, we can extract work from this and have this do some work for us. So the simplest type of redox reactions are like what I just showed, metals and their ions, right? We have zinc going to zinc 2 plus, we have copper 2 plus going to zinc solid. Zinc is a more active metal. We generally don't go over the activity series anymore in Chem 1A, but that's one of the ways to predict what we call a single replacement reactions products will be, and this is actually technically a single replacement reaction. So in this case, zinc is being oxidized because its oxidation number went from 0 to 2 plus. copper is being reduced because it's going from 2 plus to 0. And these would be the half reactions, the ones I just showed on the previous slide. So this is how we'd set this up if we actually wanted to generate electrical work and use that work. So I can put a piece of metal in this solution that contains zinc nitrate, and I can put this copper bar, right, copper metal, and put in a solution that contains copper 2 nitrate. And what's going to happen here is because I connected them with a wire, and this thing is called a salt bridge, what will happen is electrons will flow from this metal bar through the wire into this light bulb, heat up the coil, make it glow, and then go into this metal, and then move from the metal into the solution, causing the copper 2 plus in the solution to precipitate. At the same time, the electrons that left this bar, that happened every time a zinc solid went to zinc 2 plus and dissolved. So basically, as this whole thing works out, this metal bar is going to get smaller because the zinc is dissolving. And this, in this solution, we're going to see precipitate forming. Now, the salt bridge does something interesting. Usually we have KNO3 in our salt bridge because it's just the general, or really any nitrate and alkali metal in the salt bridge. And what this allows is the electrons, or the ions, every time we form a plus charge over here, a nitrate moves in to keep the charge balanced. And every time we form a negative charge, or we lose a 2 plus charge here, we get another zinc or potassium coming in, potassium ion, to keep that side balanced, because the charge needs to stay balanced, as we learned when we talked about balancing redox reactions. So this is kind of the general voltaic cell. And there's some interesting stuff that we need to talk about. There's some rules here. One of those rules is that at the anode, this is a vocab word, we always have oxidation, right? So there are two sides to that voltaic cell. One side is called the anode, the other side is called the cathode. And at the anode, in a voltaic or galvanic cell, we have oxidation occurring. In other words, the electrons are the products on the anode side of our cell. Opposite of that, the cathode is where reduction is occurring, which means the electrons are going to be the reactants in the cathode half cell. Now, generally, when we draw a voltaic cell, with a wire, right? The anode is written on the left, and the cathode is written on the right. Just as a picture, that's the general way we do it. It's a standardized thing, but it's not that big of a deal. Electrons will spontaneously flow from the anode to the cathode. Again, how does this guy get these two electrons? Well, they have to come from here, right? These two electrons move to here so that this reaction can happen. But that can only happen after this reaction happens first. Does that make sense? So if you have questions, let me know. Finally, electrons can't swim. Once the electron goes here, it's not going to swim through this salt bridge. That's not going to happen. Electrons have to stay in the metal bars or the wire that is attached to those bars. The electrons can't swim. They can't be in the solution. If you have any questions, let me know. All right. So, two half reactions in a voltaic cell are these two. So let's ask some questions about this, right? I'm telling you that. Which of these occurs at the anode? Well, as we just learned, oxidation occurs at the anode. This is an oxidation. This is a reduction. So I know that this reaction is going to be occurring at the anode because it's the oxidation half reaction out of these two. We know that because oxidation always occurs at the anode. Which electrode is consumed in the reaction? Well, now this is a little bit harder to kind of tell. We know that this was the metal electrode that we have the wire attached to. And we can see in this reaction it's going from solid state to aqueous state, i.e. it's dissolving. So again, the zinc solid anode is going to be the one being consumed. Which electrode is positive? Well, you see that we're forming electrons at the anode, and somehow these electrons are moving towards the cathode. Well, opposite charges attract. So what charge could this be if these are negative and they're being drawn towards it? The cathode is the one that's positive. Does that make sense? If you have any questions, let me know. Email, office hours, what have you. All right, so let's talk about cell notation, kind of like nomenclature when we're talking about molecules. We have ways of kind of shortcutting that whole big picture I showed earlier. So cell notation is a little tricky. It's a way of shorthand description of the arrangements of electrodes and solutions and gases represented in a voltaic cell. The cell is written starting with the anode and ending with the cathode. So as we go from left to right on our notation, we have the anode stuff first, then we go to the cathode stuff. Thus, in other words, we really care about the oxidation half reaction first because that's occurring at the anode. And then we care about the reduction second. And changes of phase are indicated by vertical lines. So for instance, let's say we're talking about that zinc solid going to zinc 2 plus half reaction. So in this type of scenario, solid, aqueous, that's a change in physical state. So what I'm going to write here for my anode is zinc solid, vertical line, zinc 2 plus, aqueous. And that would be the notation for that half reaction occurring at an anode. Then what we do is we're going to find out we have to draw our salt bridge, which we show by doing two vertical lines next to each other, and then we do the cathode after that. And we'll see this on the next slide too. Alrighty. So yeah, here's what I just drew. Okay, so a salt bridge is shown by doing two double lines vertically. So if we look at this is a cell notation. And what we have here is we start with the anode, where we have oxidation, and then we end with the cathode, where we have reduction. And in between these two, we draw these two double lines. These two double lines represent that salt bridge. Now I can build a redox reaction from this cell notation. For instance, this part I know is zinc solid because it's an anode, meaning we have to be oxidizing something, going to zinc 2 plus because that's an oxidation. And I have to add the two electrons there to get it to balance. At the same time, this one must have been Cu2 plus because it's a reduction, going to Cu solid. Again, we're reducing charge here. That's why it had to be that way. Plus two electrons as well to get the charges to balance. And then we can add these two and get the electrons to cancel and do all that from just this cell notation, which is, like we've said, a shorthand. Okay, so what happens if we don't have a solid piece of metal as part of our reaction? Like in these ones, we have solid copper here and solid zinc here. That means we can attach a wire to a solid metal electrode in these two half reactions. However, in many redox reactions, we don't have a solid present as part of the reaction. So what we do is we add usually an inert metal to stand in place of that, so that we can still connect our wire to a piece of metal so that the reaction still functions. And the usual inert electrode that's used is platinum, and it's very expensive because it's platinum. This allows for the electrons to move through the system still, even though we don't have a metal in our reaction. So if we look at this cell, this is a redox reaction. On the reactant side, we don't have a metal. On the product side, we do. So if we write the cell notation for this reaction, the first thing we need to do is we need to figure out what's being oxidized, what's being reduced. Since this has a 0 oxidation number and over here we have a +1, we know hydrogen going to H+ is an oxidation. At the same time, we have +1 going to 0. This is our reduction, right? So if we write out this cell notation, we're going to start with the oxidation or the anode, right? But we don't have a solid part of our oxidation half reaction. So what we're going to do is we're going to write platinum solid to start. Write a vertical line. Again, those vertical lines indicate changes of physical state. So I have H2 gas here. And then another vertical line to do H+ aqueous. Now we don't include the stoichiometry in cell notation generally, so this 2 here I won't include. At this point I'm done with the anode, so I'm going to do my vertical lines for the salt bridge and start on the cathode. Here's my reactant, it's Ag+ aqueous. Then we have a change in physical state, and we have Ag solid here. We don't need platinum for our cathode because we have a solid piece of metal present in the reaction, the Ag solid here. So this is the cell notation for this redox reaction. Let's do one more example. So if we have this, again, the first step is determining what was oxidized, what was reduced. I know the lead here is being oxidized because we went from 0 to 2+, and the iron's being reduced because 3+ to 2+. So we're going to start with the lead. I'm going to write Pb solid, vertical line, Pb2+ aqueous. Again, change in physical state, so we had to put the vertical line between them. I'm going to then put a salt bridge because I'm done with my anode. Now we got to talk about the cathode. Now if you look at the cathode, these are both in the same physical state and they're both aqueous. We don't have a solid here as part of this half reaction, so we are going to need to use platinum at the end here. But since they're both in the same physical state, we just list them, Fe3+, comma, aqueous, sorry, comma, Fe2+, also aqueous. Then I do a vertical line and Pt platinum solid for my stand-in electrode. Now again, these lines are only going to separate things that are in different physical states. Since both irons are in the aqueous state, we just put a comma. And it doesn't actually matter which order you put them in because we know it's the cathode, so we know the Fe3+ has to be the reactant and the Fe2+ has to be the product because that's the only way we get a reduction in the oxidation number. All right, so as always, if you have any questions at all, please feel free to email me or come to a discussion session.